Hello everyone, my name is Kai Cai. In this talk, I'm going to introduce cooperative control problems in multi-agent systems. These problems have been extensively studied in the field of systems and control over the past 2 decades. In this talk, I will try to connect the dots of several key results in these problems based on the perspective of different types of graph Laplacian matrices. Now let's get into it. From many urban environments to remote, hard-to-reach regions, multi-agent systems are transforming our industry and society. How to control them so that these agents cooperate nicely, smoothly with one another is at the center of this transformation. Let's consider a simple scenario where there are 5 rovers exploring an open field. None of the rover has access to the global coordinate frame. There might not even be one. Let's consider the simplest dynamics, where each rover is modeled as a single integrator. The state xi of t represents the 2-dimensional position of agent or rover I at time t, whose velocity is directly controlled by the input ui. Now these rovers can interact with one another only locally, and their interaction structure is captured by a directed weighted graph. Since each rover has only local information and has no access to global frame, so the control ui has to take the form of what's called distributed control, as shown here. The set script n sub I is a set of all local neighbors of rover I, namely those nodes in the graph that have a directed edge pointing to node I. And the term on the right in the bracket, xj minus xi, is the relative information. In this scenario, is the relative position that can be measured by, for example, onboard camera of rover I in its local coordinate frame. Now let's plug in this distributed control ui to the dynamics equation. We have 5 of them and stack them up. We get this compact differential equation where x here is the stack of x1 to x5. So we have 10-dimensional, each agent, each xi is 2-dimensional, so x is 10-dimensional. And the matrix L here is a so-called Laplacian matrix. So we see that the form of distributed control gives rise to the graph Laplacian. If all the weights aij's are 1, then the graph here gives rise to a graph Laplacian here. Note that every row of the Laplacian matrix sum up to 0. All the diagonal entries are positive, and all the off-diagonal entries are non-positive. So these are some characteristic features of Laplacian matrix. Now, if we simulate this differential equation from a given initial condition, namely the initial positions of the rovers on the plane, that's what happens. We can see that all the rovers converge to the same location, and this phenomena is known as rendezvous or consensus. And this is a direct result of the distributed control, where local interactions among the rovers gives rise to a global emergent behavior. Now, if we use exactly the same differential equation, but use a different Laplacian matrix. In this Laplacian matrix, still we have that every row sums up to 0, but we can have negative diagonal entry, and we can also have positive off-diagonal entries. And this is known as the signed Laplacian. So the signed pattern in this Laplacian is more or less arbitrary, although every row still sums up to 0. the interesting fact about signed Laplacian is that it can lead to a formation global behavior instead of just a rendezvous to a point. What if we further allow the entries of the Laplacian matrix to be complex numbers? And this is known as the complex Laplacian, although we still have every row sums up to 0. So this is the same across all types of different Laplacian matrices. And this complex Laplacian can also lead to a formation of a regular geometric shape. So in this talk, I'm going to introduce these 3 different types of Laplacian matrices. I'm going to call them the standard Laplacian, the complex Laplacian, and the signed Laplacian. And more importantly, I'm going to explain how these Laplacian matrices are used to achieve multi-agent behaviors from the rendezvous to what's called similar formation and affine formation. And this is part 1 of the talk, in which we are going to focus on the first type of Laplacian matrix, namely the standard type, and we will see how it's used to achieve the multi-agent rendezvous or consensus behavior. Let's start with the definition of the Laplacian matrices, which is the same across all types. So first of all, the matrix that encodes the weights on the graph is called the adjacency matrix of the graph. And then the Laplacian matrix is defined to be the degree matrix minus the adjacency matrix. This degree matrix is a diagonal matrix whose diagonal entries are the row sums of the adjacency matrix. Now, depending on the nature of these weights, Aij, if the Aij are non-negative, then the adjacency matrix A is a non-negative matrix, and the correspondingly defined Laplacian matrix L is called the standard type Laplacian, which is mostly used in the literature. If the weights Aij can be arbitrary real numbers, then L is the signed Laplacian, and if Aij can be complex numbers, then L is the complex Laplacian. Now, if we look at the rows of the Laplacian matrix, we can see by definition that the row sum, if we time the matrix L with the vector of 1, this 1 is the vector of all ones, so we are doing the row sum. The row sum, by definition, is 0. Every row sums up to 0. This means that every Laplacian matrix must have at least one eigenvalue 0, and with a corresponding eigenvector is the 1 vector, the vector of all ones. This also means that a Laplacian matrix can never be full rank. At most, its rank is n-1. For standard Laplacian, its rank is exactly n-1 if and only if the graph G contains a spanning tree. So this is a very beautiful, very neat graphical characterization of the rank condition of the standard Laplacian. And the spanning tree is a subgraph without cycles that connects all the nodes in the graph, as indicated in the green color in this 5-node example. We are going to apply this key result to establish the one-dimensional consensus problem and its solution for single integrator type multi-agent systems. And everything we are going to introduce will directly applicable to or extendable to 2D consensus and, in fact, any dimensional consensus. Let's first state the problem of consensus. Given n one-dimensional single integrator type dynamics agents, what we want to do is to design a distributed control UI such that doesn't matter where the agents start, there always exists a point C such that all the states, all the agents' state converge to that point C, as illustrated in the graph on the right. This point C is often referred to as the consensus value or the rendezvous point. For distributed control UI, we are going to use this form, which we have already introduced in the example at the beginning. So again, so here all the information is coming from the neighbors. The script n sub I is a set of local neighbors, and all the information are relative information. Okay. So now if we plug this UI back to the dynamics equation and stack them up, we can get this compact differential equation. X dot is equal to minus Lx, where this L is the standard Laplacian. Why? Because here in this UI, distributed control UI, we consider the weights Aij to be positive. So this positive weights Aij gives rise to the type of Laplacian, which is the standard type Laplacian. Here we bring in the key assumption that the graph G contains a spanning tree. By that, we know that the rank of L, we apply the result. We know that the rank of the standard Laplacian L under this assumption is exactly n minus 1. This means, in turn, that the kernel of the Laplacian L is exactly one-dimensional, and it is spanned by the vector 1, the vector of all ones. Why? Because we know that this one vector is an eigenvector for the eigenvalue 0 of the Laplacian matrix. And here, because the rank is n minus 1, we have exactly one eigenvalue 0. Okay. This, in turn, further means that for the entire system, x dot equals minus L times x, if the other n minus 1 non-zero eigenvalues of the matrix minus L, which is the system matrix minus L, are stable, namely the eigenvalues have negative real parts, then the state x will convert to the kernel of minus L, which is the same as the kernel of L, which is spanned by the vector of all ones. That means that the state will convert to a consensus. But is it true that the eigenvalues of minus L are stable except for the single eigenvalue 0? It is true, and it can be seen by Gershgorin disks. So a Gershgorin disk for a row of a matrix is a disk whose center is at the diagonal entry, whose radius is the sum of the absolute values of the off-diagonal entries on that row. So in this example, the first 4 rows give rise to the same Gershgorin disk, this red one here, centered at minus 1 with radius 1. So this disk barely touches the imaginary axis. It touches it only at the origin. Okay. The 5th row of this matrix gives rise to a second, this green Gershgorin disk, centered at minus 2, and the radius is 2. So again, it touches the imaginary axis only at the origin. The Gershgorin disk theorem asserts that all the eigenvalues of the matrix will lie within the union of all the Gershgorin disks for the rows. So in this example, the union of the 2 disks is just the bigger disk, the green disk. And we can confirm for this example that all the eigenvalues of minus L indeed lie within the green circle, including the boundary, and the boundary one in this case is exactly the origin, and we know that there is one eigenvalue 0. All the other non-zero eigenvalues are stable on the left-hand side of the complex plane or the imaginary axis. So with this pattern of the eigenvalues, we can expect consensus for this example. And indeed, we have it. starting from a given initial condition, all the states convert to a consensus value. And the conclusion that the n-1 non-zero eigenvalues of minus L are stable, have negative real parts, holds in general, exactly because of the way that the Laplacian matrix is defined. The Gershgorn disks for any standard type Laplacian will look something like this. Namely, every one of them will touch the imaginary axis, will be on the, first of all, will be on the left-hand side of the imaginary axis, and they will touch the imaginary axis only at the origin. That guarantees that all the eigenvalues will be stable except the single zero eigenvalue. So here's the solution to the consensus problem. Using this form of distributed control UI, this UI solves the multi-agent consensus problem under the assumption that the graph G contains a spanning tree. The same result extends directly to any dimensional consensus as long as this control UI is available to control the velocity on every dimension. The case of D equals 2, namely two-dimensional consensus or rendezvous, is displayed on the right. So this concludes part 1 of this talk, in which we focused on introducing the standard type Laplacian matrices, which is mostly used in the literature, and we have seen how it's used to establish multi-agent consensus problems and its solutions. So in the next part, we are going to introduce the second type of graph Laplacian, which is called complex Laplacian, and we will see the complex Laplacian matrices will lead to not only conversion to a point like rendezvous, but actually more interesting geometric patterns called formation control on 2 dimensions. So see you next time.